Swayam Prabha. Digital India. Educated India.
Okay, welcome to another class. So last time basically we ended up learning about canonical ensembles and more importantly canonical partition function, right. So we defined canonical partition function. And we denoted it by Z, which was basically sigma of exponential of minus beta times epsilon I. So this is basically e raised by minus beta epsilon I, where epsilon I are all the energy states that are present in the system, right. And another important result that we got in the last class was we saw that the variance of energy in a canonical partition can be written as kBT squared times Cv, where Cv is the heat capacity of the system at constant volume, right. So it gave us a very fundamental or first principle way of understanding the meaning of the heat capacity of systems, right. Okay. And later we basically moved on to later we basically asked ourselves whether we can derive the ideal gas equation through the concepts of statistical physics, right. So essentially what we did, so we wrote the partition function for an ideal gas in the following way. So e raised to the power minus beta E, where now the sum corresponds to summing over the energy states of all the gas molecules in the ideal gas, right. So basically this sum runs over energy states of all gas molecules, okay. And we saw that since in an ideal gas it's like ideal situation where the particles are not interacting with each other and they are the contribution to the internal energy comes only from the total kinetic energy of all the gas molecules. So we saw that we can simplify this expression to look like this, e raised to the power beta epsilon, where epsilon is now the average energy of one gas molecule, and now the sum runs over energy states of single molecule, and we can just multiply this thing by n times, and this is how we can write down the partition function. And remember, epsilon is the average kinetic energy of single gas molecule, okay. And essentially we basically determined this quantity, we just summed over all the microstates, right, all the microstates which are present in the phase space, right. So we wrote it in this way. So 1 divided by h cubed and the integral on space, which basically is over volume V, and there are 3 integrals in the momentum space times e raised to the power beta p squared divided by 2m, where p squared by 2m is the energy term, right, and this whole thing raised to the power n. And when we simplified it, we saw that this can be written as V divided by h cube times 2 pi m kBT raised to the power 3 by 2, and this entire thing raised to the power n. And this was the important result that we had last time, right. And remember beta is basically, okay, so beta is 1 by kBT, okay, that is shorthand notation for beta for kBT, okay. And later what we did, we basically wrote down the Helmholtz free energy as minus kBT times log of z, and when we did this thing, so we saw that we can write down in this way. So this is kBT times n, and we conveniently split this term into a term which contains only V and another term which contains all the other terms which do not have V in them, V in it, right, kBt divided by h cube raised to the power 3 by 2, right. And the reason for doing this was because we were interested in the term pressure, which is negative of partial derivative of free energy with respect to volume at constant temperature and n, and when we take partial derivative with respect to V, this term gives you 0 and you end up with kBt V by n, and finally we got a result PV equals n kBt, and this is indeed the ideal gas equation that we expect, right. Okay, so this is where we ended our class last time. So this indeed this formulation of statistical physics indeed gives us the right results, at least in when applied to systems which are like ideal gases, all right. And along the similar lines, we can also calculate another quantity which is the average energy of the ideal gas, right. So in the last class we also obtained a result that average energy in a canonical ensemble can be expressed as minus del by del beta of log of partition function, right. And this is we also argued that this is basically the internal energy, so basically internal energy per molecule in thermodynamics, right. Okay. All right. Actually, since Z already has n in it, so this actually will be the average internal energy, average energy, right. Okay. So and now again we can now plug this value in here. So we can use the expression for Z that we got here. Okay. So we can so from this equation we can take its partial derivative with respect to beta, all right. So let me write it in this way. Okay. So this is nothing but minus del by del beta of log of Z. So I am just taking log of this term, I am taking n in front and I am writing 1 by kBt as beta. Okay. So there is a little bit of algebra going on, n times log V by h cube times 2 pi m 3 by 2 plus log beta raised to the power minus 3 by 2. Okay. So again I have done this trick where I have separated the term which only contains beta and all the other terms are outside, are like taken out of that single term. Okay. And the advantage of doing is that this will directly give me 0 and here I will get 3 by 2 beta times n, right. And since beta is 1 by kBt, this is nothing but 3 by 2 times n times kBt. Okay. And again like this is n times 3 by 2 kBt, and we know from equipartition theorem that the average kinetic energy of single molecule with 3 degrees of freedom. So remember when we were evaluating this integral, we used 3 Gaussian integrals, right, which correspond to the translational degree of freedom along x, y and z, right. So we did not consider any higher order energy terms in the so we did not consider any rotational or vibrational modes in the system. Okay. And this can be written as n times epsilon due to equipartition, right. Okay. So therefore this is also what we expected, right. So we know that the internal energy of an ideal gas molecule of an ideal gas is basically 3 by 2 times number of molecules times kBt, right. So this is what we expected, all right. So basically we will come back to this formulation again. So far we have shown that everything is going very fine and things are like all making sense, they are in accordance with the thermodynamics and kinetic theory, but we will see there we will run into a little bit of problem in a minute. Okay. But before that we will discuss quickly about the grand canonical ensemble. Okay. Grand canonical. Okay, maybe I can go to the next page. Basically grand canonical ensemble. So, again the way we were considering, so consider we have a huge system which is insulated and isolated, it does not exchange any heat, as a result of which its total energy does not change, the total number of particles remains constant and its volume also does not change, right. So, it has certain total energy E, certain number of molecules N, and therefore, the number of microstates which is omega total, which is a function of its energy as well as the number of particles, all right. And now, we have our much smaller subsystem of interest, which is inside, which has small which has some energy which is epsilon, and number of particles which is n, and corresponding number of microstates is omega 1, which is a function of epsilon and n. And outside we have the reservoir, right. So, this is the reservoir with the total with energy E minus epsilon, and the number of particles in the reservoir is n, n reservoir minus n, right. So, let us call the total number is n reservoir, all right. So, okay, and the corresponding number of microstates in this system is omega 2, which is a function of E minus epsilon and n reservoir minus n, all right. So, now again we will basically go along the similar lines as we did for micro canonical as well as canonical ensemble. So, we are interested in the probability to find this system, okay. And on top of that, I think that I forgot to mention. So, this system is an open system, right. So, there is energy exchange as well as particle exchange is allowed, right. So, here so subsystem 1 can exchange heat and particles with the reservoir with the basically subsystem 2, right, with the bigger system 2. Okay, that is the difference. So, in canonical ensemble we did not let n fluctuate, but here n can also fluctuate, right. And we know, like we learnt in the in the canonical ensemble, there were huge energy fluctuations, right. So, in fact, the distribution of this energy was an exponential distribution rather than having a well defined peak along, as we saw in the micro canonical ensemble, and that distribution was basically decided by the temperature of the bigger system 2, right. So, essentially this small system was in contact with a bigger system which was at constant temperature T, and constant because we assume this subsystem is so small that any amount of energy exchange does not really change the temperature of this bigger system. However, in this case now we are like going more general in some sense. Now, we have opened this system up and we are saying like the number of particles can also go in and out, right. And in equilibrium, the distribution of this number of particle obviously will not be decided by temperature, but that will be decided by the chemical potential of the subsystem 2, right. So, that is exactly what we will do, right. So, therefore, we can again write, so the probability to find subsystem 1 to have energy epsilon and particles n, that can be written as P of epsilon and n, and this is basically equal to all the microstates that correspond to that condition, epsilon n times omega 2 E minus epsilon n reservoir minus n divided by total number of microstates, which is omega total, and this is E and n reservoir. Okay. Now, again we will do basically the similar calculation that we did for canonical ensemble. So, we will take log on both sides. So, taking log on both sides, right. So, this can be written as log of P of epsilon n basically is equal to log of omega 1 epsilon n plus log of omega 2 E minus epsilon n reservoir minus n minus. So, this term is constant because this is completely isolated system, right. So, there is some constant which we are ignoring, right. Now, remember we are always assuming that this subsystem 1 is much smaller than subsystem 2, right. So, since this system is much smaller than this system, this approximation is always true. So, epsilon is much smaller than E minus epsilon, and the number of particles in this subsystem is also much smaller than n reservoir minus n, right. So, this system is in all sense it is much greater than this system, bigger than this system, all right. So, therefore, what we can write is we can just assume that this term is much smaller than this, and log of p of epsilon and n basically is just scales with log of omega 2, which is a function of E minus epsilon and n reservoir minus n, all right. Okay. Again what we will do is, so in the canonical ensemble we Taylor expanded our this term around epsilon equal to 0, all right, because we assume that the energy is so small we can always expand it around epsilon equal to 0. But now since the particle exchange is also allowed, we also have to expand it, Taylor expand it around the condition where n is almost equal to 0, right. So, basically so Taylor expand log of omega 2 this term, right, around epsilon equal to 0 and n equal to 0, right. And if we do that, we can write this term. So, log of omega 2 of E minus epsilon and n reservoir minus n evaluated near epsilon 0 and n 0 can be written as log of omega 2 E minus epsilon and n reservoir minus n evaluated at epsilon 0 and n 0 plus E minus epsilon minus E times partial derivative of log of omega 2 with respect to E, again evaluated at epsilon equal to 0 and n equal to 0 plus the second expansion, right. So, n reservoir minus n reservoir partial derivative with respect to n reservoir of log of omega 2 evaluated at epsilon equal to 0 and n equal to 0, plus of course, there will be higher order terms which we are ignoring, right. So, we are assuming epsilon and n are much smaller. So, we can ignore all the higher order terms, right. So, all the higher order terms which we are neglecting, all right, and this can basically be written as approximately equal to log of omega 2 which is now a function of E and n reservoir, right, minus epsilon times partial derivative. So, these two things cancel out, right. Similarly, this cancels out of log of omega 2, right, minus n times partial derivative with respect to n reservoir of log of omega 2. Okay. And we know by definition, right. So, since by definition, we know so partial derivative of a quantity which is like log of number of microstates is basically 1 by kBt, right, and partial derivative of the same quantity with respect to now number of particles is negative of chemical potential divided by T 1 by kBt, right. This is what we saw in the earlier classes. Okay. So, therefore, if we substitute this definition back there, right, and we can write, okay. So, therefore, we can write log of omega 2 which is a function of E minus epsilon and n reservoir minus n is basically equal to log of omega 2 of E and n reservoir minus epsilon divided by kBt, I am substituting for into that, plus mu n divided by kBt, right. So, I have just substituted these definitions back into this equation, right. And since we know that this log of P of n is basically determined by log of omega 2, so I can write this implies, so I can just write log of P of epsilon and n, like the log of probability to observe our subsystem to be at energy state epsilon with number of particles n is basically log of omega 2 E and reservoir minus, so I am taking out 1 by kBt and calling it beta times epsilon minus mu n. Okay. And finally, the final result that we get is P of epsilon n can be written as omega 2, which is function of E and n reservoir exponential of minus beta epsilon minus mu n, mu n. Okay. So, this is the desired probability that we wanted. This is for grand canonical, right. This is the case for grand canonical ensemble. Okay. So, remember now we also had a similar looking term in canonical ensemble where we had omega 2, which was function of energy of the bigger system, right. And so, which basically tells you that in order to evaluate the probability for your system to be in any state, you have to have knowledge of all the number of microstates or all the complicated things that are happening in the bigger system, right, and which is not really a practical thing to do, right. So, therefore, we come up with a alternate solution. Basically, we use the condition of normalization of these probabilities and we can essentially write that the probability for this system, our system to exist in any particular energy state epsilon I with number of particles n I is basically minus beta. Okay. So, basically that can be written as omega 2 times which is a function of E and n reservoir times e raised to the power minus beta of epsilon I minus mu n I divided by sum of all other probabilities, right. So, I can take out omega 2 outside E and n reservoir and I can sum over all the other energy states. So, basically minus beta epsilon 1 minus mu n 1 plus e raised to the power minus beta epsilon 2 minus mu n 2 plus so on plus e raised to the power minus beta whatever, right. So, so on up to whatever final number of, I can just leave it like that, right. So, it is basically summing over all the energy states, and the advantage of doing that is these two terms cancel out and we can just replace it by e raised to the power minus beta of epsilon I minus mu n I divided by now we can define this term as the grand canonical partition function ZGC, where ZGC is sum over all the energy states and the number of particles, the states of number of particles times e raised to the power minus beta times epsilon I minus mu n I, right, and this is known as the grand canonical partition function. Okay, I do not have space to write here, but this grand canonical partition function. Okay, so, this is another very important result. Okay. So, now let us now use this result to calculate some quantities, right, in the grand canonical ensemble. All right. So, the first thing that we can do is we can now calculate the average number of particles. Okay. So, average number of particles in the smaller subsystem, right. So, basically what we are saying is since this subsystem is much smaller, so these particles are getting exchanged all the time, right. If this system was much bigger, just like we did in microcanonical ensemble, so the fluctuations around some average number would have been very tiny, right, because the system will have some average number of particles with a well defined peak, right. But since this system is much smaller, it is exchanging number of particles with the other outside system all the time. So, again the distribution of this number of particle will be similar to energy distribution, which was exponential, right. Okay. So, this can be actually shown, which I am not really doing. but now what we can still define is what is the, at any given moment, what is the average number of particles which are existing in this small subsystem, all right. So by definition we can see that quantity average n is basically sum over the probability to find particles in that state Ni times the number of particles, right. So this is by definition, okay. And now what we can do is we can now substitute this value here, okay. So this is basically equal to Ni times now the definition. So basically the probability using the partition function. So e raised to the power minus beta times epsilon I minus mu Ni divided by z, okay. Z here is now the grand canonical ensemble, and I will very quickly show that this can be written as a partial derivative with respect to mu of log of z at constant beta, okay. And let us see how, right. So how, okay. So here we can see that del by del mu of log z is basically, if I just do the evaluate this differential, this is 1 by z del z by del mu, and now I will substitute for the z. So this is 1 by z and del by del mu of sigma I e raised to the power minus beta Ni minus epsilon I minus mu Ni, right. And if I take this derivative with respect to mu, so I get sum over I 1 by z. So this term comes in front, okay. So this term comes in front. So this is since okay, so this is there is no minus here, so this is beta times Ni, okay, because there is minus and minus here, times e raised to the power minus beta times epsilon I minus mu Ni, right. And I can now simplify this in a little way. So this is beta times sum over I Ni divided by z e raised to the power minus beta epsilon I minus mu Ni, right. And if I take this beta, okay, and this is basically so this term is basically similar to this term, right. So this is Ni e raised to the power minus beta this thing divided by z, this is also Ni e raised to the power beta divided by z, and this is beta times that, okay. So therefore our main result is that the average number of particles can be written like this, all right. So okay, and remember this derivative was evaluated at constant beta, okay. So that is why there is a beta in here, all right. So okay, so the next thing that we can do is we can also calculate the average energy in a grand canonical ensemble, all right. So average energy in grand canonical ensemble, okay. So this average energy epsilon by definition is sigma I P of epsilon I times epsilon I, right. And again the same exercise essentially. So if we just take sigma over I, so I am just replacing my P of epsilon I, which is epsilon I times e raised to the power minus beta epsilon I minus mu Ni divided by z, okay. All right, and I will show you that this basically can be written as partial derivative with respect to beta of log z plus mu n, okay. And let us see how, right. So how is that? So how? So let us evaluate this first quantity. So right, so negative of del by del beta of log z. So, I can write as minus 1 by z del z by del beta, okay, and this is minus 1 by z del by del beta of sigma I e raised to the power minus beta epsilon I minus mu n I, right. And if I evaluate this derivative, so this just can be written as I 1 by z. So, there is minus sign, so this that disappeared, times epsilon I minus mu n I times exponential of minus beta epsilon I minus mu n I, okay. And this I can split into two terms, right. So, the first term is sum over I epsilon I by z e raised to the power minus beta of epsilon I minus mu n I minus mu times sum over I n I divided by z e raised to the power minus beta of epsilon I minus mu n I, okay. And this you can see that by definition this is actually equal to the average energy, right. So, this is the average energy, right. So, this is that term. So, this is average energy, like this is the same term as we have written here, minus mu times, and this is by definition is the average number of particles, right, in the system, okay. And which implies my average energy, right, this is what we are interested in, becomes minus, okay, I am taking now this term to the other side, negative of del log z by del beta plus mu n, okay. So, where when I wrote n, that is basically the average number of particles, right. So, this is the final result, okay. So, let me write it properly. So, this is plus mu n, okay. So, we can do this simple exercises to now evaluate the useful quantities in the grand canonical ensemble just by using the partition function, the concept of partition function, okay. All right. So, this was all about grand canonical partition, but now let us go back to the canonical ensemble again, all right. So, basically back to canonical ensemble. Okay. All right. So, I'll maybe write it one more time. So, remember in the canonical ensemble we defined our partition function as sum over energy states of all molecules, right. So, sum over states of all molecules of the quantity which looks like e raised to the power minus beta times E, and we argued that in an ideal gas in an ideal gas we can just replace it with the e raised to the power minus beta times epsilon raised to the power n, and now the sum does not run over energy states of all the molecules, but this sum is only on the states of single molecule, right. And when we did that we basically found the expression for the partition function in canonical ensemble to be V by h cube times 2 pi m k b t raised to the power 3 pi 2 and the entire thing raised to the power n, okay. So, this is what we found, okay. And remember what we did in the last class, we used this partition function to derive the ideal gas equation as well as to show that the average energy of an ideal gas at a given temperature is basically 3 by 2 times the number of particles times kBT, right. So, something which agreed with our notion, right. But now let us see whether we can extend it further, right. So, let us see whether we can calculate the entropy of this gas, okay. So, now we know from thermodynamics, right. So, from thermodynamics, so the differential of the Gibbs free energy is basically written as minus S dt minus P dV plus mu dn, right, and which implies I can define my entropy in the following way. So, this is negative of partial derivative of Helmholtz free energy with respect to temperature at constant volume and number of particles, all right. And since we know, so the F in the canonical ensemble is negative of kBt times log z, and we saw in the last class this is minus kBt times n times log of V by h cube times 2 pi m kBt raised to the power 3 by 2, all right. Now, let us take partial derivative. Okay. Now, basically what we are doing is we are going to evaluate the expression for entropy from this F, right, and for that we have to take its partial derivative with respect to temperature while keeping the volume and the number of particles fixed, right. So, taking partial derivative with respect to temperature. Okay. So, so we can see that in this case the entropy which is minus del F, which is del F by negative of del F by del T, right. So, this negative sign drops out. So, we are left with so basically kBt and kBt. So, first I am going to take derivative of this So, there are two terms which contain temperature, there is one temperature here, there is another here. So, first I am taking derivative here. So, n kBt times, okay. So, what I can do is I can always write, so I can always split my log term, okay. So, maybe I can do that. So, this is minus kBt times n log of so log of t raised to the power 3 by 2 plus log of all the other terms which do not have t, right. So, I have just very conveniently picked out t out of this factor, right, and all the other terms. So, this is n kBt. I am taking first the derivative with respect to of this term. So, this becomes times 3 by 2 and 1 by t, right. So, derivative of log of t is 1 by t plus now I can take the derivative of just this term. So, this is n kb times log of this entire term V by h cube times 2 pi m kBt raised to the power 3 by 2, okay. And you can see here the temperature cancels out. So, I am left with, maybe I can write it on the next page. So, this is 3 by 2 n kb. So, remember this is entropy plus n kb times log of V by h cube times 2 pi m kBt, this thing raised to the power 3 by 2, okay. So, now let us examine this quantity carefully, right. So, clearly we see that okay. So, there are a lot of problems with this term, right. So, remember according to third law, so the entropy of the gas or any system should go to 0 as temperature goes to 0, right. But here we see that as T goes to 0, in fact, the entropy not only does not go to 0, but the second term is not even defined, right. So, we have log of 0, right. So, S is not defined, right, since log of 0 is a problematic quantity, right. So, of course, you can argue that so whatever calculation we have done it for a gas, right, and at T equal to 0 everything should solidify, right. So, this should break down in the even in the very beginning. We can't even use these concepts down to temperature T equal to 0. So, whatever approximations we have made to calculate this quantity, that should not even work at t equal to 0, right. So, but there is a bigger problem, right. So, which we will now talk about, all right. So, let us see what is the bigger problem. So, there is a bigger problem when we think about mixing two ideal gases, okay. So, let us see what that is, all right. So, let us do an experiment, right, of mixing two ideal gases, mixing of two ideal gases. Okay, so let us do that, all right. So, say we start with a system, right, divided into two portions. So, on the left side we have n1 number of particles of molecules with mass m1, and the volume of this part of the container is V1, and let us for simplicity assume that this is at temperature T, all right. So, again let us assume like this system is not exchanging heat or anything, right. So, this is all isolated system, okay. And on the other side we have n2 number of molecules with mass m2, and the volume of this part of the container is V2, and say this is also at temperature T, right. And say we immediately like we say we remove this partition instantaneously, we remove this partition quickly, okay, and then we end up with a situation. So, again I will right. So, this is okay. So, now we end up with an ideal gas with number of molecules n1 plus n2 with volume V, right. So, volume V which is V1 plus V2, and the mass we have two molecules which have mass m1 and mass m2, right, and we have a temperature still T, right. So, temperature will not really change, okay. So, let us calculate the entropy change in such a process, right. So, let us calculate the total entropy before mixing, right. So, this is before mixing, okay, and this is after mixing, okay. So, initial entropy before mixing, so let us call it SI, which is basically the sum of entropy of 1 and 2, right. So, S1 plus S2, okay. So, now let us use this formula to write down the entropy expressions, right. So, this can be written as 3 by 2 N1 Kb plus N1 times Kb log of log of V1 T raised to the power 3 by 2. So, I have like separated the term V times T raised to the power 3 by 2, and all the other terms which contain mass, they have like fundamental constants in front, right, 2 pi h cube and Kb, right. So, I can just write it as N1 Kb log of some constant times mass m1, right. So, all this constant includes all the terms which have h cube, 2 pi and Kb and so on, okay. This is for the first system, plus for similar term we can write for the second system, like second part of the system N2 Kb plus N2 Kb log of V2 T raised to the power 3 by 2 plus N2 Kb log of similar thing. So, constant C times M2, right. So, this is the initial entropy before we have done the mixing. So, what is the final entropy, right? Slightly better manner. So, this can be basically written as N1 Kb times 3 by 2 plus log V1 T raised to the power 3 by 2 plus log of Cm1 plus N2 Kb 3 by 2 plus log of V2 T raised to the power 3 by 2 plus log of Cm2. Okay. Now, let us calculate the entropy in this state, right, after the mixing has happened, right. So, after mixing, So, what is the entropy, right? So I can write my SF as 3 by 2 N1 kb plus N1 kb log of V t raised to the power 3 by 2 plus N1 kb log of Cm1 plus 3 by 2 N2 kb plus N2 kb times log of V raised to the power 3 by V times t raised to the power 3 by 2 plus N2 kb times log of Cm2, right. So, what basically I have done is, now all these gas molecules, they have volume V, right, to move around. So, therefore, I have basically written down V1 and V2 as V for both the species, right, both 1 and 2, all right. So, therefore, now we can basically calculate the change in entropy, right. So, the change in entropy, that is delta S, which is SF minus Si, right. And now if you see that there are most of these terms will cancel out, all right. Most of these terms will cancel out, like this term here, all these constants will basically cancel out, and will basically will be left with the quantity which looks like this. So, N1 times kb times log of V minus log of V1 plus N2 times kb of log of V minus log of V2, okay. And this can be written as N1 kb times log of V by V1 plus N2 kb times log of V by V2, okay. So, now let us simplify this even further, right. So, let us assume, assuming N1 is equal to N2, right. So, say the number of particles were equal in both the compartments, right. Similarly, let us assume that M1 was also equal to M2, say they were both same gases, right, the same species, okay. And also assume V1 is equal to V2, which is equal to V by 2, right. So, say we divided this system into exactly into half, all right, and if we put these numbers there, so what we get is the change in entropy basically becomes, so let me call this N, let me call this M, right. So, N times kb, so V by V1 is basically log 2, right, plus N kb log 2, which is 2 times N kb log 2, all right. And this is actually a problem, because if you now think about this process, so what exactly have we done? So, we had a situation where there were on average equal number of particles, okay. So, we had a situation where we divided this system into half, basically into two equal halves with equal number of molecules on both sides, and those molecules had the same mass, right, and they were at the same temperature, right. And this is something that we anyway expect in equilibrium, right. So, if in this room I just put a hypothetical wall here, at any given moment there will be equal number of gas molecules on both sides of the wall, there will be the temperatures of both the walls will be equal, and of course, the volume is already half. So, this wall, this hypothetical wall is not really going to change the equilibrium situation, right. So, the system is going to remain in equilibrium throughout this process, right. So, this mixing will not really lead to any entropy production, because the system remains in equilibrium all the time, right. So, since the system is expected to remain in equilibrium, we so delta S should be 0. So, this is should be, but we are not really getting 0, right. So, there is this problem, right. So, this is a problem, okay. So, that is one problem that we have when we use this approximation, that we can just write our partition function of the ideal gas, where earlier we were summing over all the molecules, but then we made an approximation that we can just do the sum over states of single molecule and just raise to the power n, and the partition function that we got, even though it gave you the right ideal gas equation and average energy, but it failed at giving you the right basically the right expression for entropy, which should go to 0 as t goes to 0, as well as the right expression for entropy, which should have captured the entropy change of such a mixing process to be 0, but we did not get 0, right. And also let us see another problem actually, right. So, we also saw that okay. So, let us look at the expression for the Helmholtz free energy, all right. So, I am just going to rewrite this expression on the next page. So, okay. So, let us write Helmholtz free energy as minus n kBT log of V by h cube times 2 pi m kBT raised to the power 3 by 2. Okay. Now, let us see what happens if I take n to 2n, right. So, if we make n 2n, okay. So, what happens to f? Okay. So, you can see okay. So, remember this Helmholtz potential, Helmholtz free energy, these are extensive variables, right. So, they should scale with the system. So, if you increase the number of particles in the number of molecules in any system by a factor of 2, so this energy should also scale with a factor of 2, right. So, you can see that if I do that, so what happens is the new f becomes minus 2n kBT log of, but remember there is another very inconvenient quantity sitting in the parenthesis, which is volume, right. So, if you increase the number of particles by if you double the number of particles, then the volume also increases by the factor of 2, right. So, volume is another extensive quantity. So, this becomes 2V by h cube whatever times 2 pi m kBT 3 by 2, right. So, therefore, it is not really scaling with 2, because there is another inconvenient factor of log of 2 in the parenthesis, right. So, which implies f is not an extensive quantity. So, it indeed is increasing or its magnitude is changing is increasing as we increase the number of particles, number of molecules, but it does not really scale with 2, because we have an inconvenient factor of 2 sitting in the log as well, right. So, since it does not become 2f, right, it should have given us a result which was twice of the old f, right, but we are not really getting that. But you can very easily see if there was an n sitting in the denominator. So, let me put it with yellow color. So, if we had an expression which is v divided by n h cubed, right. So, when I make n to 2n, so this 2v will become 2, so this v will become 2v, and you will also have correspondingly 2n, and this 2 would have disappeared, right, and that would have given you the right result, right. So, therefore, it seems like we can fix the partition function if we divide by n somewhere in our calculation, right. And basically we will see how we can do that. Okay. So, we will basically come back to this thing again, and basically it boils down to the concept of distinguishability and non-distinguishability, which we can discuss in the next class. All right. So yeah, so I will end my class here. So, in the next class we will basically try to see how how we can basically we will start working towards fixing this problem, and we can understand what is the concept of distinguishability and non-distinguishability. So, essentially what has happened here is we have assumed our gas molecules to be distinguishable, but in fact they are not really distinguishable. All right. So, we will see if we take that into account, we can fix this problem. All right. So, thank you so much.